Thank you for the introduction. So I'm Aviv Tamar. I recently joined Technion after a post at Berkeley, and I had the robot learning lab at Technion. And today I'll tell you about work that started at Berkeley and is ongoing progress. And it's called Visual Planning for Robotic Manipulation. Now, as you probably know, robots are very good today at performing repetitive tasks. For example, car manufacturing. But in the future, we'd like robots to work in the wild. For example, in our homes or in hospitals, or walking alongside humans. So this is very challenging. What if we want, for example, a robot to cook our meal or make our bed? Well, we need to deal with unstructured environments, tasks that change all the time, and we need to manipulate objects, for example, this pillow, which is very hard for robots today. So how can we tackle this problem of autonomous decision-making in unstructured environments? Well, there's been a lot of work on this. Most of the previous work tried to model the world as some kind of controlled dynamical system. The robot can take actions, it affects the state of the world. The robot can perceive its environment, take observations, and it needs to select actions based on its observation to achieve some goal. So a goal could be, for example, a reward function, or some constraints that have to be met, or things like that. And most of the work on this topic has been under a setting that I'll call here classical planning and control. The setting assumes that we know the model in the environment and we know the perception model. And then this becomes kind of a search problem. How do we find the actions that move the world to a certain state that we want? And this has been very successful, but assuming that we know a model for the state and the perception is just too limiting for real-world problems in unstructured domains. So here's an example. This is an example of a peer-to robot setting a table, a classical task and motion planning formulation. And a typical state in this world would be whether the robot is holding a cup or not. And this is a good state when we try to model the problem, but it's not necessarily a good state for the robot, which needs to actually infer whether it's holding the cup or not. And for vision, this could be a pretty complex task. So recently, there's been a lot of work on reinforcement learning to kind of go around the modeling problem. And reinforcement learning actually says, I don't want to model at all. I'm just going to learn a direct mapping from my observations to actions that that solve the task. And I'm going to do it using trial and error, guided by some reward function. And this is great. And this is the reason that many people in robotics are now looking at reinforcement learning. But there are some caveats. For example, the fact that we have a reward function means that we are only learning the task that we have a reward for. And it's often difficult to define a reward, for example, if you have image-based inputs. Also, RL is very data demanding. We need a lot of trials. And in general, it seems like a very weird decision-making process because as humans, we try to avoid trial and error as much as we can. So basing all our decision-making process on it seems like a strange thing to do. There's also model-based reinforcement learning, which in principle has the best of both worlds. We learn a model from data, and we use planning on that model. And in some problems, this worked great, for example, flying a helicopter. But again, when we have high-dimensional observations like images, we don't really know how to make this work yet. The most complex problem we can solve right now are kind of pushing objects to some positions. Definitely not as complex planning that we can do when we know the model. So all of these approaches have some fundamental drawback when it gets to having autonomous robots that solve general tasks in unstructured environments. And today I'll suggest a different approach, which is slightly different than all of these. And to motivate it, I'd like to ask you, let's do a simple experiment. Here's an image of a rope. And I'd like you to imagine, as vividly as you can, how you would manipulate this rope into this simple loop shape. Really have the mental picture in your head of how this rope changes. You can also do this for a simple knot that we do every day. Let me ask you maybe a slightly more challenging task. Can you imagine how to manipulate the rope into this knot? You see on the bottom. Well, I'm sure that after a few minutes or seconds, you'll be able to solve it. And the point here is that as humans, we have a very strong capability to imagine our actions, plan with them, And probably this is a fundamental principle that we can use to solve the decision-making problems. So what we wanted to ask is whether we can replicate this imagination principle in robots. So to do this, we came up with a problem formulation that we call visual planning. And here's the idea. We're going to let the robot play with some object. For example, here is this rope. It's called a self-supervised learning. The robot is programmed with a very simple policy to pick up the rope at a random location, move it slightly, and release it. And it works for days. And this is data collected from, this is a paper by Nair et al., not our work. They collected this data about the rope, and now we want to process it into some kind of model. So we assume that our data is pairs of observations from this collected data. The idea here is that pairs of observations has some information about the physics of the rope, some causality, what can happen before something else. So for example, we know that the rope can split in half or can't move too drastically in this type of environment. Now what we want to do is I'll give you a starting image, and then I'll give you a goal image, and I want you to imagine all the missing images in between that goes from start to goal. Now this has to satisfy the physics of the rope that we saw in our data. So for example, it can't just move or split in half or something like that. It has to move in small increments as we saw. Now, if we can solve this problem, then we have a very good basis for later doing control. So we can use it as a reference signal, for example. And note that this formulation abstracts away all the control problem and just focuses on the essential problem about how to understand how an object behaves. So our inspiration for solving this problem came from recent work on GANs, or deepfakes, as you probably all have heard of. And we know that we can look at data of images, for example, and then imagine different images that look at our data, and we can also interpolate between them in a very smooth manner. So we thought, well, maybe you can do this for the rope. Maybe you can train data on this rope images and then use the interpolation for planning. So again is composed of a generator and a discriminator. It takes as input some random noise. A generator network transfers it into an image, and a discriminator tries to distinguish between real images and fake images. And by playing this game between generator and discriminator, we converge to real data distribution. So we train again on this data, and we try to interpolate between start and goal, and it didn't really work that well. And this makes sense because the GAN never understands anything about the transitions if it's trained this way. It just generates images. Well, we thought maybe we can add more structure to the GAN, and there has been work on that. In particular, work called InfoGAN looks at the mutual information between the observation and the input to the GAN, and this has generated GANs that have particular states that control, for example, the shape of the objects or their orientation. And we did that, and it still didn't work because, again, it doesn't care about the transitions, just about the structure. So we came up eventually with a model that we call Causal InfoGAN. And the idea in Causal InfoGAN is that instead of generating one image, we generate pairs of images. So by generating these pairs, we have to capture the physics in the data. We have to capture what image can come before the other. And we also have mutual information between pairs of states that generate the data. And we structure this states, the transition between the states, in a particular way that will allow us later to plan. Here we'll plan using linear interpolation. So we structure the transition to be local perturbations of the state such that interpolating between them will always have a high probability in our data. And here's an example what Causal InfoGAN generates. It's much better. Here are some more examples of different types of rope shapes. All of these were not seen. These are trajectories that were not seen in the data. Our model learns to imagine the possible sequence of transitioning the rope from start to goal just based on random data that it saw. We also verified numerically that this has a much better performance than standard models. Now, so we see that this can actually learn to imagine rope manipulation. It's actually a more general model, so I'd like to kind of revisit this model and go to the components of it to understand what it can do. So the novelty here is both the generating two images, looking at the mutual information between them and starting the states that drive this model. So let's first look at the mutual information. How do we maximize mutual information? Well, we base our approach on prior work by Chen et al., which proposed a variational principle for maximizing mutual information. Basically, it means that we also train an encoder Q that maps from the observation back to the state that generated it. Now, what are these states that I am talking about? So basically, we want these states to capture 10 more minutes. These states would capture the transition that generated the pairs of observations that we saw. And we want them to be, first of all, back-probable, so we can actually train this using gradient descent. And we want them to be plannable, so we can later plan a sequence of images. So this could be any model that satisfies these will be good for us. So for example, we can apply this for a binary state space, and then this would be similar to a representation that you use in classical planning, where we have predicates, but here we would be learning these predicates just from our data. And we can train these models using stochastic neural networks. So I want to show you an example of this kind of model, just as a toy example to understand how general this model is. So this is just a particle moving in two-dimensional space. We get data from randomly moving this particle, and we want to train this causal InfoGAN model with a discrete state space. So what does a discrete state space mean here? It means that we're actually clustering this two-dimensional map into some clusters. Now, we made this map in a very particular way where a Euclidean distance measure is not informative. Notice that there are two tunnels that are not connected, but are very in close proximity. So if you look at standard clustering algorithms for this task, they will cluster those tunnels in the same state, which is definitely not relevant for planning using these clusters. Now, causal InfoGAN actually looks at pairs of transitions. Now, it never saw a transition from top to bottom, because that's not possible in our data. So it understands that the clusters should obey the actual physics in the domain. And then we can use this for planning. So how do we plan? We take our started and goal observations, we map them to their started and goal states using our classifier Q. Then here we plan using search on a graph. And then once we have a plan in the latent space, we map it back to observation space using our generator in the GAN. So here's, for example, how it looked like. These are start and goal positions, and these are the trajectories that it generated. You see that it never found a trajectory to the bottom goals because that's not possible in this model. So this is just an example of generality of this model. What I showed you before with the rope images is the same model. The planning is a little bit different just because it worked better for images to use a different, not use the classifier for encoding, but we actually search for the best encoding, and we use linear interpolation for planning, and this results in what we saw before. Now, so we have a method for imagining visual manipulation. How can you use it for actually controlling or acting on the system? So actually, it's pretty simple. Once we have a visual plan, we can just track it. So if in our data we recorded our pairs of observations and the action that brought the first observation to the second, we can train something called an inverse model. This is just supervised learning, learning what action generated O prime from O. And once we have that, we have our image reference trajectory on the top here. We look at a current image, use the inverse model to calculate our current action that takes us towards the reference plan. We observe our new image and sequentially repeat that until we track the plan. You can also replan, but we actually didn't need that here. So here's an example in a simulated domain. These are just two blocks that can move. We have image observations of this. We train a causal InfoGAN model, and then we plan or imagine how the movement should look like, reaching from start to goal. And then we use an inverse model to actually carry out this plan, and you see that it tracks it rather nicely. We compare this to reinforcement learning. Now, the the relevant comparison and reinforcement learning here is off-policy batch reinforcement learning, which takes all this data and tries to find a policy. We also need a reward function at states for the reinforcement learning, so we used a recent method that was suggested for this by training a variational autoencoder and looking at reward as distance in the latent space of the VAE. It didn't work well. We got to about 15% success, while our model got to 90% success. We then started adding more clues for the reinforcement learning agent. We fed in the real reward and the real positions instead of the images, and eventually we got to around 75% success, which is still worse than our model. The reason is that our model understands that the blocks can fall off the table because it never saw this in the data. The reinforcement learning agent here always had some problem with pushing the blocks off because it never understood that this shouldn't happen. Next, here, this is the real deal. We wanted to show that this can work on a real robot. So we revisited the rope manipulation problem that I showed you in the beginning. And we actually made it a little bit more challenging. We added obstacles, this yellow and red obstacles that we can move them on this breadboard. And now we want the robot to imagine and carry out a plan for manipulating the rope on this domain. For handling the obstacles, we wanted to show that this can generalize in a zero-shot sense. That means that we train on some obstacle positions, but now we see a different obstacle positions, and we want to generate plans that take that into account. This was actually pretty simple. We just needed to add another context to our causal InfoGAN model. Here, the context is the image of where the obstacles are. And now all the generations need to take this image into account. For planning, well, you can imagine that interpolation won't be a very good idea because we have obstacles now. So we went for a slightly more complex transition model with a neural network that predicts the transitions, and we used A-star planning, and we made these transitions local by regularizing the neural network so that it's still very local perturbations. This way we can use the Euclidean distance as a heuristic function for A-star. Now everything here is learned. The transitions are learned, the latent space is learned, but eventually we get some planning that is not interpolation that learns to move around these obstacles. And here's everything all together. We first play with the rope to generate some data. Then we plan or imagine our plan using causal InfoGAN. We get something that looks like this. And then we use our inverse model to carry out the plan, which is what you see here. So on the right, you see the plan that we imagined. On the left, you see what the robot is seeing from its camera. And you see that it's trying to follow the plan that it imagined beforehand. Now, to my knowledge, this is the first demonstration of a robot that actually imagines its plans and carries them out all from raw image data. So I have to say this is still a work in progress. This can solve relatively simple planning problems around these obstacles, and we need to improve the success rate of this. But I think that the implications here are pretty strong. So, for example, this is a very safe approach. Before we carry out any robot experiments, we can actually visualize what robot is planning to do. And if it doesn't look right for us, we can stop it. This proved to be a very useful concept for model selection. Usually when you train something for robotics, you have many models, many parameters you can choose. And then you need to select the best one based on robot experiments, which is very expensive and time consuming. Here we can visually inspect what models were good by just looking at the plans that you generate, which allowed us to really save a lot of time and get this project running in a very small amount of time. I think that having a robot that actually produces an interpretable plan of what it does is a very important factor for future research. So we've proposed this framework, which is an alternative to off-policy RL that we call visual planning. The main benefit here is interpretability. We can see what we plan before we actually take any action. It's also generalizable in the sense that we don't have any reward function. We just look at a goal image and we plan towards that. And it's modular in the sense that we don't care about actions here. So this is not limited to a particular robot. We just learn what the rope can do when we manipulate it, and then we let, after we imagine what the rope needs to do, in some sense, we let the robot actually carry out that plan, which is very similar to, I think, to the way humans think about problems. So there's a lot more work. We believe in this method, and we're now trying to make it more popular. So the first thing we're doing is having some formal benchmark where people can try out the methods. It's a simulated benchmark, and it's still work in progress, but here's some example domains that we're looking at. So here, for example, is a task of moving this green block around this red obstacle that can have different shapes. On the bottom is a task of moving some weird-looking shapes through an opening. But the idea here is that you need to look at the images, and from the images understand the kind of physics that goes on here. So, for example, what is the geometry of the shape that is relevant to moving it in the correct orientation through this opening. Another thing that we are looking at is what is the correct performance measure here. So in RL, we typically look at success rates. How good did I perform the task? But here we also want to look at how good our imagined plans look. So this is more similar to what we do in image generation in GANs. So we want to look at some perceptual score of how good our visual images are. How am I on time? Oh, not. So it'll be a little bit early. All right. So there are still some more challenges. The main challenge that we faced is after we imagine a plan, figuring out which image transitions are actually not possible. So when you have a model, the model will always sometimes be wrong. And we want to find that out. So the good news about this is that this is exactly a novelty detection problem. So we have some data of pairs of images that are correct. We generate some pairs of images from our model and want to see which of them make sense and which of them doesn't. The bad news is that novelty detection in images is still quite a difficult problem. There's been a lot of recent progress recently, and we are also pushing in that direction ourselves. And I think that this is also a very important problem for general reinforcement learning, where in general we have some kind of model. We want to figure out when it's correct and when it's wrong, and we still don't have very principled ways of doing that. Other challenges here is first how to generalize in a zero-shot sense. So we showed some preliminary results with the obstacles, but basically if I train on a rope and I understand how the rope works, and now I see some other flexible object that looks like a rope, I want to be able to generalize to that as well. Now this is a pretty difficult problem. Another thing is how to handle multiple objects. So obviously when you have multiple objects interacting, the difficulty of the problem grows exponentially. And we're actually looking into approaches that classical planning people looked at. We're using object-oriented representations and things like that. But this is still a very open problem. Another open problem is how to handle cluttered scenes. So here everything was from an overhead camera where we on a green background. Cluttered scenes is very challenging. And also once the camera starts moving, it's unclear how to extend these methods to that. So to summarize, we propose a problem that we call visual planning, where the idea is that we want to learn how to imagine images in a goal-directed way. So we have a start image and we have a goal image, and we want to imagine images in between. And this is an instance of decision-making with high-dimensional observations that looks at the essence of the problem. We don't care about actions, we don't care about the robot, we just care about what is the actual physics model in our problem, how do we capture it from our data, and how to use it for planning. The main benefits of it is that it's interpretable and safe. So once we can imagine what the robot is going to do or what the robot wants to do, we can have a human operator that looks at that and intervenes if that's necessary. Our model for solving visual planning is called Causal InfoGAN. That's only one way of solving this task. But in Causal InfoGAN, the idea is to train a GAN, deep generative model, that can explain dynamical systems by looking at pairs of images and by structuring the latent space in the GAN so that it's easy to plan with. And we show that we can plan using graph search or interpolation or A star. And this is actually a general concept that you can extend to other planning algorithms. And in some sense, this bridges between work on classical planning and modern work on deep representation learning. And to summarize the whole thing, we started by outlining these different approaches: classical planning, model FRL, model-based RL, and showing that each of one of them is in some sense limited. And I think that visual planning has the best of all of these worlds. So in some sense, we work on real image data. It's not limited to known models or known perception models. It can handle whatever observation you feed it. And there's no reward to guide it. It's based on planning towards a goal. And there's a very clear definition of generalization. We want to generalize to goals that we haven't seen in our data. This is very different than model FRL. And you can think of a more general lifelong learning approach here, where a robot would kind of pick up more and more models of objects as it learns, and then uses these models to solve problems that it hasn't seen before, potentially eventually solving things like cooking or making a bed or other problems in our house. So, thank you all. I'd also like to thank my collaborators that worked on this.
Do you have a question for Liv?
What a question here.
Hi. You mentioned that you used GAN for generating rope states. And now, then you mentioned that you know also the inverse function led to that state, right? Did I understand you correctly?
The inverse model looks at pairs of images.
Yes.
The inverse model looks at pairs of images and outputs what action moved the first image to the second image. So when we collect the data, the robot looks at the rope, takes an image, moves it a little bit, and then takes another image. So if we just record the action, we have data that looks that consists of image, first image, second image, and an action that moved from one first to the other. So this becomes just a standard supervised learning problem.
Thank you. Is there another question? No. Thank you very much.